Last lesson we talked about different types of force, and this lesson we're doing about something called resultant forces. So lots of forces act on an object. So it's not just one force. And these forces might act in lots of different directions. So you might have forces down and up and left and right and forwards and backwards and all of that. So we can consider the size and direction of the forces. And so let's remember, if it has size and direction, then that means it's a vector quantity. So we did about that in the first lesson of this topic. So remembering that force is a vector, which means that direction matters. Okay, and we can replace all of these forces, all of these different forces, with one single force, and that single force is called the resultant force. Okay, so we can consider the size and direction of these forces to replace it with one single resultant force. Okay, so resultant force is the kind of key term for this, and it just means the kind of overall force that takes into account the size and direction of all the other forces that act on it. So what does this look like? Well, we're going to split this up into balanced forces and unbalanced forces so that we can kind of have a look at it. And kind of true tradition, we're going to think about a box and somebody pushing a box. So now I have to draw. We know that my art skills are terrible. Okay, they look like they've got a broken leg, but never mind. So we've got somebody pushing a box, and we're going to say that they are pushing forwards with a force, and there is a force acting in the opposite direction, which in this case would be friction. Okay, so if these forces are balanced, then balanced forces, then there is going to be no resultant force. So let's remember from probably year 7 when we did forces that the size of the arrow represents the size of the force. We can see that these arrows are the same size and they're in opposite directions, so they will cancel each other out completely, which means that they're balanced, and it means that there is no resultant force overall. Okay, so we need to know what happens when there's no resultant force, when the resultant force is 0, and this is basically Newton's first law of motion. So we talked last lesson about one of Newton's other laws, but this lesson we're talking about Newton's first law of motion, which is basically that if something is stationary at rest, it's going to stay at rest if there is no resultant force. So if it's stationary, it stays at rest, and if it is moving, it moves at a constant speed. Okay, so if there's no resultant force because the forces are balanced, then either it's going to be stationary or it's going to be at a constant speed, and which one of those depends on whether it was stationary to start off with or whether it was already moving. Okay, so this person who's pushing this box, if the box is stationary and they're trying to get it moving in the first place, the box is still going to be stationary. But if they're already moving the box, then this box is going to be travelling at a constant speed. So it does depend on the context, and in an exam question they would tell you about the context, so you need to read really carefully to make sure that you've understood whether or not they're talking about something that is going to be stationary or whether it's going to be moving at a constant speed. So now if we think about unbalanced forces, so let's have our box and our person pushing. Okay, so now they're going to push and they're going to be pushing more. So the forward force is going to be bigger, but the friction is going to be the same. So for this, because the size of the arrow represents the size of the force, okay, we can see that, and they're in opposite directions, therefore it's going to be the difference between these two sizes that is the resultant force. So if we kind of look at this orange arrow, if we moved it, if we like looked at what proportion of the pink arrow it kind of takes up, so going up, that means that that part of the force would be cancelled out by the orange bit. Okay, so the resultant force would be this bit that's left over. Okay, so if they're in the opposite directions, then it is the difference between the two arrow sizes. If they're in the same direction, then we just add the values together. Okay, and we can think about what happens with the motion for this box as well. So in this case, this box would be speeding up because they're pushing it in this direction and there's a resultant force in the direction they're pushing it. So therefore this box would be speeding up. So that's this example, okay? But it could be slowing down if it was a situation where, if we've got a pink arrow, if our orange arrow was bigger, then it could be slowing down if there was an unbalanced force on it. Okay, so I think the next topic that we talk about motion. So we talk about objects moving, speeding up, slowing down, travelling at a constant speed, and we'll look at motion graphs. But all of it does link together, and you could be asked questions in your exam that link together the forces that are on an object and the motion. So always think about whether it's going to be balanced or whether it's unbalanced. If it's balanced, it's either going to be stationary or travelling at a constant speed. If it's unbalanced, then it's going to be speeding up or it's going to be slowing down, depending on which direction the resultant force is in. I'd like to do some questions. As we've done before, if I'm going to read out the question and highlight it, and then it would be good for you to pause the video, try and answer the question, and then listen to the answer. The first 5 questions are essential, so I'd like you all to do them, and then the questions after that are going to be the extension task. So a cyclist on a bike has a thrust force forward of 1,600 newtons and the wind blows towards him with 500 newtons force. So it shows us on the diagram as well, 1,600 newtons this direction, 500 newtons in this direction. What is the size and direction of the resultant force? So they're in opposite directions, so as we discussed before, we're going to find the difference between these. So we're going to do 1,600 minus 500, which we can use a calculator for, to get 1,100. So that's the size of the force. And then the direction is going to be in the direction of the bigger arrow. So we can just say to the right. In the grid below, each square represents 1 Newton of force. State the size and direction of each force arrow. So let's look at arrow A first. So this one. So first of all, we'll count how many squares it is. So 1, 2, 3, 4 squares. So each square is 1 Newton, so it'll be 4 newtons, and the direction is to the right. Remember that we do from the bottom of the arrow to the very tip of the arrow point. And then for arrow B, we're going to count again. 1, 2, 3, 4, 5. So 5 newtons to the left. Two forces of 15 newtons and 36 newtons are acting on a body. Calculate the possible resultant forces and directions when the forces are acting in the same direction and in opposite directions. So if I've got 36 newtons and 15 newtons in the same direction, then we're going from left to right. Then we're going to add them together. So 15 plus 36 is 51. So we'll have 51 newtons to the right. And if they're going in opposite directions, then we're going to find the difference between them. So 36 minus 15 is 21. And this is going to go in the direction of the 36 Newton force. Okay, so it depends on which, it doesn't give us a direction of that one, but it would be in the direction of the 36 Newton force. Okay, so we have a diagram of a car, and it gives us two values here, 2,000 newtons, 500 newtons. What is the value, size of the resultant force on the car? Show your working. So they're in opposite directions, so we're going to do the difference. So 2,000 minus 500, which you might be able to do without your calculator, but let's do it anyway. 2,000 minus 500 is 1,500 newtons, and that's in the direction of the bigger force, which is the 2,000 Newton one, so we can say to the right. So describe the motion of the car. Well, as we looked at before, if it's in the same direction that the car is travelling, which it is, then it will be speeding up. Or accelerating. Okay, so question 3. A plane has a weight of 300,000 newtons and a lift of 300,000 newtons. The thrust is 500,000 newtons and the drag is 200,000 newtons. What are the resultant forces on the plane and how will they affect the plane's motion? Okay, so let's consider these in terms of pairs, like opposite pairs. So we've got lift going up and weight going down. Well, lift going up is 30,000 newtons and weight going down is 30,000 newtons. So actually that's going to be 0 resultant, 0 vertical resultant force. Okay, and then we've got 500,000 newtons. Oh, it says 500,000 newtons here, but 50,000 there. I think that that's an error. So 500,000 newtons forwards and 200,000 newtons backwards. Oh, they've just missed a 0 off both of them. Oh well. Because they're in opposite directions, we're going to find the difference, which again, you'll probably be able to do without your calculator, but let's just do it anyway. Which is 300,000 newtons. So in this case, we could say, so it's going to be in the same direction as the thrust, which is to the left. We could also say forwards, because that's the direction that the plane is facing in. And how will it affect the motion? Well, if it's got a resultant force forwards, then that means it's going to speed up, but it's going to remain at the same height. Okay, so now we've got a diagram of the box, and it's asking us, what is the resultant force on the box? In which direction will it move? We need to consider the forces. So we've got 2 forces going to the left and 2 forces going to the right. So we need to do a couple of different steps for this. So first of all, we need to work out the overall force to the left and the overall force to the right. So we can do that by adding these together. So if we do 14 plus 5, then 14 plus 5 is 19. So we've got 19 newtons overall going to the left, and then to the right we've got 7 plus 5, which is 12. And then we need to find the difference, because these are in opposite directions, we need to find the difference between these two. So we would do 19 minus 12, which is 7. And it's going to be to the left because this has the biggest overall force. There's another way that you could have, so it will be going left, that's the answer to that question. There's another way you could have worked this out, which is by looking at this and seeing you've got 5 newtons going to the left and 5 newtons going to the right, so you could have said they cancel each other out, which then means you're just comparing the 14 newtons left and the 7 newtons right and finding the difference between those, which is still 7. So this one's a little bit more complicated. We're going to find the resultant forces and in which directions will it move. So there's a clue here already, and it says forces and directions. So we're expecting that there's going to be more than one kind of force, so it's not just going to be in one direction, left or right, like the one above. But we're going to do the same strategy and look at the opposite kind of pairs of forces. So we've got 6 newtons going to the right, so let's have a look at what we've got going left. We've got 12 and 3, so we're going to do 12 plus 3 is 15. Okay, so this isn't going to be balanced. We've got 15 and we've got 6, so we're going to find the difference between those two. So 15 minus 6 is 9, which is going to be to the left because 15 is on the left. And then we've got 18 newtons down, and then we've got 6 and 3. So 6 plus 3 is 9. Which is up. So we're going to do 18 minus 9 because they're in opposite directions, so we're going to find the difference, which is also 9 newtons down because 18 newtons is bigger. So it's going to move left and down. So it's going to move diagonally like this because it will move a bit left and a bit down, which means it's going to move in a diagonal direction. These are the extension questions. So look at the diagram below. The biker has put the bike in gear and he is turning the throttle slowly to apply a slight driving force, but he is also applying the front brake. The bike is not yet moving. These questions are about the effects of forces in equilibrium. Label the 2 forces acting on the motorbike in the above diagram. So we've got a forwards force, which is the driving force, because it's given to us in the question, slight driving force. He's also applying the front brake. Well, we can call that a braking force, that's fine. Okay, the 2 forces on the motorbike are in equilibrium. Explain what this means. If they're in equilibrium, that means they're equal and opposite. So they're balanced. Describe what will happen to the motorbike if these forces remain in equilibrium. So if there's no resultant force, then it's going to stay as it is, and it's not yet moving, so that means it will remain stationary. So these questions are about the effects of resultant forces. The biker now releases the front brake. Describe how the motion of the bike changes. Okay, so if he releases the front brake, so we get rid of this force, there is now a resultant force forwards, which means he's going to speed up. Different backwards forces now act on the bike. Name one of these forces. So any force that opposes the motion. The first one we should probably think of is friction. We could also say drag, or air resistance. So hopefully we remembered that from last lesson. Eventually, the backwards force becomes equal to the forwards force. How does the motorbike move now? So when it gets to a point where the friction and the air resistance and everything that's moving in the opposite direction to the driving force is equal, then it will move at a constant speed. So look carefully at the forces applied on the plane below and answer the following questions. Label all the forces acting on the plane on the diagram. We had another question about a plane, so this should be quite easy. So we had lift here, and we had weight. And then we had thrust and drag. So the plane's facing this direction now, so this would be thrust, and this would be drag. The plane is flying along a horizontal line. Describe the motion of the plane in this situation. So if it's describing the motion, whenever it says motion, we're talking about speed and we're talking about direction, really. So it's saying that it's flying horizontal, so it's not moving up, it's not moving down. So really we're now thinking about what's happening to its speed. Well, we've got 58,000 newtons forwards and 12,400 backwards, so they're unbalanced, so therefore it's going to be speeding up. I've just spotted that that's the next question. So the next question, calculate the horizontal resultant force. Well, they're in opposite directions, so they're different, so we're finding the difference. So 58,000 minus 12,400. So 45,600. 45,600 newton. The runner in the picture is running with the wind pushing her forward. The backwards friction force on the athlete is 42 newtons. The forwards force of the wind is 21 newtons, and the force from her muscles is 84 newtons. Complete the diagram by adding force arrows to show the forces acting on the runner. So adding force arrows. Make sure the arrows are about the right length. Okay, so we need to draw some arrows. We want to make sure they're about the right length. If we want to make sure they're about the right length, we need a ruler. Okay, so we've got to add 3 arrows. So the backwards friction force on the athlete is 42 newtons. So if we do a centimetre is a newton is probably the easiest way. So if we've got 42 newtons, that would be 4.2 centimetres. So let's do that from where her foot is. 4.2 centimetres. And we would label that friction. There's a forwards force of the wind is 21 newtons, so that would be 2.1 centimetres. So the wind's probably going to push her about here. Well, it's going to push her all over, but let's just draw it here. So it's going to be a forwards force. And then the force from her muscles, which is going to push her forwards, is 84 newtons, which would be 8.4 centimetres. Oh, I can only just get it. 8.4 centimetres, so muscles, wind. Okay, so get used to using a ruler and a pencil to draw like arrows that are as accurate as possible in terms of length. And now we need to calculate the resultant force on the runner, give its direction. So forwards, we have 84 plus 21, because that's the wind and the muscles, which is a total, 84 plus 21 is a total of 105 newtons. And then backwards is 42, so we need to find the difference between these two because forwards and backwards are opposites. So 105 minus 42 is 63. Okay, so there's going to be 63 newtons forwards, which is to the right in this diagram. So describe and explain how the results of these forces, explain the result of these forces on the motion of the runner. Describe and explain the result of these forces on the motion of the runner. Okay, so there is a resultant force forwards, okay, and so the runner will speed up. So these are the kind of basic parts, but for 4 marks we need to add a bit more detail. So there will be a resultant force forwards, because we've just worked that out, and she is going to speed up, but she's not going to be able to speed up forever. The more the speed increases, then the drag increases as well. So drag increases, and so that means that the acceleration is going to decrease until she runs at a constant speed. And then the summary. So the resultant force is a single force that has the same effect as all the forces acting on an object. If this is 0, the object is stationary or travelling at a constant speed. If this is greater than 0, the speed or direction of an object will change.